Mount Rainier stands above the Pacific Northwest with an unmistakable presence, its snow-covered summit visible from cities, forests, river valleys and coastlines stretching across Washington state. On most days it appears timeless and motionless, a towering monument sculpted by thousands of years of volcanic activity and relentless glaciation. Yet modern instruments reveal a reality hidden from every pair of human eyes. Deep within the mountain, tiny vibrations continue to ripple through ancient rock, producing faint seismic whispers that can only be detected by an extensive network of sensitive monitoring stations. During the past 2 weeks, scientists have documented 41 small earthquakes clustered beneath Mount Rainier's summit region. 4 additional tremors have been recorded during the most recent 2-day period, continuing a sequence that has drawn the attention of volcanologists and seismologists alike. None of these earthquakes have been large enough to be felt by nearby communities, yet each one contributes another piece to an evolving picture of activity occurring beneath one of the most closely watched volcanoes in the United States. According to regional seismic monitoring, the earthquakes remain shallow and concentrated beneath the summit area, a pattern commonly observed during volcanic earthquake swarms. The numbers themselves may appear modest when compared with destructive earthquakes that capture international headlines. A sequence measured in dozens of tiny tremors rarely dominates news broadcasts. Mount Rainier, however, is no ordinary mountain. Rising approximately 14,410 feet, or about 4,392 meters, above sea level, it is the tallest volcano in the Cascade Range and one of the most heavily glaciated peaks in the contiguous United States. The combination of volcanic heat, massive ice fields, steep terrain, and densely populated river valleys has made Rainier one of the world's designated decade volcanoes, a recognition reserved for volcanoes capable of posing significant hazards because of both their geological history and the number of people living nearby. That distinction means every cluster of earthquakes, no matter how small, receives careful scrutiny. Inside laboratories, monitoring centers, and university research facilities, the arrival of each new seismic signal is automatically logged by computers before being reviewed by specialists. Every waveform is examined to determine its origin, depth, magnitude, and relationship to surrounding events. Patterns matter far more than individual earthquakes. One isolated tremor often means very little. Several occurring within hours of one another may suggest an entirely different process. A cluster extending across days or weeks becomes another chapter in the long-term record that scientists use to understand the volcano's behavior. Earthquake swarms differ from the more familiar sequence of one large earthquake followed by numerous aftershocks. Instead, swarms consist of many earthquakes occurring close together in both time and location, without a single dominant event leading the sequence. Volcanoes around the world frequently produce these swarms, and Mount Rainier is no exception. Historical records reveal that similar episodes have occurred repeatedly during the modern monitoring era, often lasting several days before gradually fading back into the mountain's normal background activity. For people living in nearby communities, the appearance of fresh tremors naturally raises concern. Rainier's silhouette dominates the skyline from Tacoma, Seattle, Olympia, and countless smaller towns. Families hike its trails, climbers attempt its icy slopes, and millions visit the national park every year. The volcano is woven into everyday life throughout western Washington. News of renewed seismic activity therefore spreads rapidly, often accompanied by anxious questions about whether an eruption is becoming more likely. Scientists are careful not to jump to that conclusion. Volcanoes are dynamic systems that remain active long after their last eruption. Heat continues to circulate beneath their surfaces. Water seeps downward through fractures before interacting with hot rock. Steam accumulates, pressure shifts, minerals alter surrounding rock, and fluids migrate through cracks that have existed for thousands of years. Every one of these processes can produce tiny earthquakes without requiring magma to rise toward the surface. That distinction is among the most important lessons modern volcanology has learned. Mount Rainier's current sequence resembles patterns that researchers have documented many times before. Previous swarms beneath the volcano have often been attributed to the movement of hot fluids circulating above the deeper magma storage system, rather than fresh magma forcing its way upward. These fluids, heated by residual volcanic heat, travel through fractures in the crust. As pressure changes and rocks adjust, small earthquakes occur. The resulting seismic signatures can resemble those produced during volcanic unrest, making careful analysis essential before drawing conclusions. Even so, every swarm represents an opportunity. Each earthquake acts like a tiny flashlight illuminating part of the mountain's hidden interior. Seismic waves travel through rock at speeds influenced by temperature, density, fractures, and fluid content. By measuring the arrival times of these waves at numerous monitoring stations, scientists gradually improve their understanding of the complex plumbing system concealed beneath Rainier's frozen summit. Over decades of observation, that knowledge has grown tremendously. Only a generation ago, many earthquakes beneath volcanoes would have gone completely unnoticed. Modern digital seismometers now detect events so small that hikers standing directly above them remain entirely unaware anything has happened. Instruments continuously transmit information to monitoring centers, where automated software immediately searches for new activity. Human analysts then review the data to verify locations and identify emerging trends. Mount Rainier benefits from one of the most comprehensive volcano monitoring systems in North America. The mountain is observed not only through seismic instruments but also by ground deformation sensors, satellite measurements, gas monitoring, thermal observations, and visual surveillance. No single instrument tells the complete story. Instead, scientists compare every available source of information before evaluating whether a volcano is behaving normally or exhibiting signs of escalating unrest. At present, those additional monitoring systems have not indicated that the volcano is progressing toward an eruption. During previous swarms, the United States Geological Survey emphasized that the observed activity remained consistent with the normal background behavior for Mount Rainier, and that alert levels did not require escalation. Earthquake swarms alone, particularly when composed of very small events lacking accompanying deformation or increased volcanic gas emissions, do not necessarily indicate magma is approaching the surface. That measured response reflects decades of experience gained from volcanoes across the globe. Some volcanoes erupt with remarkably little warning. Others experience months or even years of restless seismic activity without producing an eruption at all. Separating those possibilities requires patience rather than speculation. Mount Rainier's geological history offers another reminder that volcanic systems operate on timescales extending far beyond a human lifetime. The volcano has experienced eruptions during the Holocene, with its most recent recognized eruptive activity occurring roughly 1,000 years ago, although historical reports from the 19th century describe possible steam emissions and other observations that continue to be discussed by researchers. The mountain remains classified as an active stratovolcano, meaning future eruptions are expected at some point, even if no one can predict precisely when. Its greatest danger, however, may not come from explosive eruptions alone. Rainier supports an enormous volume of glacial ice spread across its upper slopes. If volcanic heat, landslides, or structural collapse were to rapidly melt portions of that ice, the resulting lahars could race down surrounding river valleys with devastating speed. Geological evidence demonstrates that enormous mudflows have occurred repeatedly throughout the volcano's history, reaching far beyond the mountain itself and reshaping entire landscapes. Because thousands of people now live atop ancient lahar deposits, emergency planning focuses heavily on these secondary hazards rather than ash alone. For that reason, even seemingly minor earthquake sequences receive careful attention. Scientists understand that public confidence depends not on predicting every event perfectly, but on recognizing meaningful changes as early as possible. Every additional tremor is compared with years of archived data. Magnitudes are plotted, depths are calculated, epicenters are mapped, frequencies are analyzed. The emerging pattern is then weighed against decades of previous swarms beneath Mount Rainier and similar volcanoes throughout the Cascade Range. The result is a cautious balance between vigilance and perspective. Neither complacency nor alarm serves the public well. Instead, the mountain is watched hour after hour, day after day, through an uninterrupted stream of data flowing from instruments quietly operating across snowfields, forests, and rocky ridges. Hidden beneath one of North America's most recognizable peaks, the latest sequence of earthquakes continues to remind scientists that although Mount Rainier appears peaceful from a distance, it remains a living volcano whose internal processes never truly come to rest. Although the latest sequence has remained modest in size, volcanic earthquakes are never dismissed as meaningless background noise. Every tremor adds another measurement to a continuous record that helps scientists recognize whether the volcano is behaving within its expected range or beginning to shift towards something more significant. Experience has shown that volcanic systems often communicate through subtle changes long before dramatic events unfold, making persistent monitoring one of the most valuable tools available for protecting nearby communities. Mount Rainier is monitored around the clock by an extensive network of seismometers operated by the Pacific Northwest Seismic Network and the United States Geological Survey. These instruments are capable of detecting earthquakes far too small for people to feel, allowing specialists to locate each event with remarkable precision. Sophisticated computer systems continuously scan incoming data, automatically flagging unusual activity before trained analysts verify earthquake locations, estimate magnitudes, and compare the results with decades of historical records. This combination of automation and expert review ensures that even minor changes beneath the volcano receive careful attention rather than being overlooked. The recent count of 41 earthquakes over the past 2 weeks, including 4 during the most recent 2-day period, has therefore become part of a much larger scientific picture rather than an isolated statistic. Researchers are examining whether the events are tightly clustered beneath the summit, whether they are migrating in depth or location, whether their frequency is increasing or decreasing, and whether other monitoring systems are detecting corresponding changes. These questions are essential because earthquakes alone rarely provide enough evidence to determine whether magma is moving toward the surface. Volcanologists instead rely upon multiple independent observations that work together like pieces of an enormous puzzle. If magma begins rising through the crust, it often produces additional signals beyond earthquakes. The volcano may begin to swell as molten rock accumulates underground, a process known as ground deformation. Satellites orbiting hundreds of miles or hundreds of kilometers above Earth can detect tiny changes in the volcano's shape that would otherwise remain invisible. Highly sensitive global positioning system receivers anchored to solid bedrock can measure movements smaller than the width of a fingernail. Instruments that analyze volcanic gases watch for changes in emissions of sulfur dioxide, carbon dioxide, and other gases that frequently accompany magma approaching shallower depths. At Mount Rainier, these complementary monitoring systems are just as important as the earthquake record itself. If seismic activity were accompanied by measurable inflation of the volcano, increased gas emissions, changing temperatures around fumaroles, or persistent volcanic tremor, scientists would begin evaluating whether the volcano was entering a higher level of unrest. At present, however, the available information does not indicate such a combination of warning signs. The recent earthquakes remain consistent with episodes that have occurred before at the mountain without leading to an eruption. That conclusion is supported by the volcano's own history. Mount Rainier has experienced numerous earthquake swarms during the decades of modern monitoring. Many lasted several days, while others persisted longer before gradually fading away. In most cases, researchers concluded that the earthquakes resulted from the circulation of hot fluids through fractures within the volcanic edifice rather than the upward movement of fresh magma. Heated groundwater can create pressure changes deep inside the volcano, causing surrounding rocks to crack and shift slightly. These tiny fractures release seismic energy that instruments record as earthquakes, even though the overall volcanic system remains stable. Understanding this distinction is crucial because not every active volcano behaves in the same way. Some volcanoes produce long periods of elevated seismic activity before erupting, while others generate similar earthquake swarms without progressing any further. The challenge facing volcanologists is determining which patterns represent ordinary internal adjustments and which signal a genuine escalation. That is why scientists emphasize trends instead of focusing on a single day's earthquake count. A few additional tremors rarely change the overall assessment unless they are accompanied by broader changes throughout the volcanic system. Rainier's immense size also contributes to its complexity. The volcano contains an intricate network of ancient lava flows, solidified magma bodies, hydrothermal systems, and fractured rock that has evolved for hundreds of thousands of years. Heat remaining from past volcanic activity continues interacting with groundwater circulating beneath the summit. This hydrothermal system is capable of generating earthquakes independent of eruptive activity, making careful interpretation of seismic data especially important. Despite the reassuring assessment surrounding the present swarm, Mount Rainier remains one of the most closely watched volcanoes in the United States because of the hazards it poses should conditions eventually change. Its steep slopes support enormous glaciers containing vast quantities of ice. Even relatively small volcanic disturbances or large landslides have the potential to generate lahars, fast-moving mixtures of water, mud, volcanic ash, and rock that can travel many miles or many kilometers down river valleys. Geological evidence shows that such flows have reached areas now occupied by thriving communities, underscoring why emergency planning extends far beyond the boundaries of the national park. For residents living in Western Washington, the latest earthquakes therefore serve less as a signal of immediate danger than as a reminder that Mount Rainier remains an active volcano deserving constant observation. Modern monitoring technology provides scientists with an unprecedented ability to detect subtle changes beneath the mountain, offering valuable time to evaluate developing conditions should more significant unrest ever emerge. Until then, every newly recorded tremor contributes another line to a scientific record that grows more detailed with each passing year, strengthening the understanding of one of North America's most iconic volcanoes while helping ensure that any meaningful change is recognized as early as possible.